Hello guys, how you doing today? I hope you're doing well. I wanted to do a little bit of review of materials that were on the first test because they're going to appear again on the second, third, and final. So let's make sure that we've done that. And then we'll go ahead and get started on lecture 4. So I'm going to go ahead and share my screen over here. All of what I'm going to show you today is in the lecture 4 notes, but it is a little bit separate from what we talk about in lecture 4. So we're just going to do the beginning portions of this now. Okay? So, what are we talking about? What is Avogadro's number? So, Avogadro's number is one of those things that you probably should know. The number is 6.022 times 10 to the 23rd particles per mole. Okay, awesome. We can do that. What is the molar mass of arsenic? Well, strangely enough, the molar mass should be found on the periodic table. I understand that there was no periodic table on the test. I made an assumption, and we all know what happens when we make assumptions. I made an ass of you and me, and things didn't go as well as they probably should have. Now, having said that, I know that that's an issue. How do I plan to deal with that? Well, I'm going to give you some questions through D2L that would give you an idea of what a test would look like if you had a periodic table. And I will post to D2L periodic table that I'm planning on giving you and some information sheets. Now, unfortunately, I can't attach that to the test. So what I can do is give them to you on D2L. You will then need to print them so that you will have them during the test. I will make notification of this on the website soon. I promise. The other thing, because we did have issues with the first test and people were not able to do as well as they probably should have, I'm going to do what's done in some of the other classes that are held by the department. And I'm going to say that if your first test ends up being your lowest test score, whatever grade you get on the final can replace that test score. Okay? If your final grade is a higher grade, it will replace your first test. Okay. Now, if you get a lower grade on any other test, then your final grade will replace that. Okay. So that's how we're going to run that. If there are any questions or comments, problems about that, then let me know and we'll talk through it. Okay. All right. So having said all that, let's talk about arsenic. Now, I happen to have a big, huge periodic table here that I keep on my desk. Arsenic is number 33. It is in group 15 or VA, and its mass is listed as 74.92 grams per mole. Okay? So, yay, that's awesome. Next question that we have. I have 15.362 grams of beryllium. How many moles do I have? And how many particles is that? Well, if I want to talk about that, then we need to pull up some scratch paper, so we can do that. And I'm also going to pull up my calculator so you can see what I'm doing on my calculator. Now, the way that I handle all of these calculation problems that we do is to write down any information that's given to me. And I tend to write it in a particular order because that helps me to solve the questions, solve the problems that we're looking at. So let's take a look at this. 15.362 grams of beryllium. And I want to know number of moles, number of particles. Okay, awesome. I can do that. I know how to go from grams to moles. In order to do that, I need to take the mass that I have, because I always start with the information that they give me, and then I convert it. And the way that I convert it is by using the molecular weight. Well, Be is element number 4. It is in group 2A, and its mass is 9.01 grams per mole. Okay, grams cancel with grams, and that's going to give me an answer in moles. So 15.362 divided by 9.0. All right, well, let's turn our calculator on because that would be useful. 15.362 divided by 9.01 gives me 1.70 and some change. And if I have to look at the number of sig figs that I have, my mass that I started with is 5 sig figs, but the molecular weight that I have from the periodic table is only 3. So that's going to be reported as 1.70 moles. Now, in order to go to particles, I know that I need to know the number of moles to be able to do that. And so that's an extension of the calculation that I've already done. In order for me to do that calculation, I can either take the result that I just found, and multiply that by Avogadro's number, or, and this is the way I always do it, I indicate the part of the calculation that I've already done Now, why do I do either one of those things? Well, okay. This way, where I use the result that I used before, is perfectly acceptable, and it's been written with that number rounded. It's perfectly acceptable to write it like that. But you know that when you do this calculation, you need to work with all of the digits that came out of your calculator to do the next portion, okay? So that's why I don't choose to write it like this, because that implies to me that I don't need those digits, and I do actually need them. 15.362 grams of BE divided by 9.01 grams per mole times 6.022 times 10 to the 23rd indicates that I can do that as one calculation, and I absolutely can. So I can either set this up so that I take that number and then I multiply that by 6.022 second e to the 23rd, or I can do it as 15.362 divided by 9.01 times 6.022. Got to hit the second to the 23rd. Notice I end up with the same number as long as I've taken all of those digits. But what happens, let's just, for the sake of argument, do this as 1.70 times 6.022 to the 23rd. I don't get exactly the same answer. Now, does it matter? That depends. For 3 sig figs, no, it doesn't, because you end up with the same number at 3 sig figs. Although, does it actually? If I were to round this to 3 significant digits, 1.026 rounds to 1.03. 1.023 rounds to 1.02. And this is what I was talking about those rounding errors. That's why we need to carry all those digits that we have here, okay, or in the result that we got here that we rounded, but we don't actually want to round when we're doing it. So that's the reason I carry that calculation. Now, both of those are going to give me the same number. Oh, and I'm going to round 1.03, and again, it's 3 sig figs because the 9.01 grams is only 3 sig figs. And this is 10 to the 24th particles. Okay? So that's not only my number of moles, but also my number of particles. And I hope that that demonstration will show you why we need to carry all of those digits down through it. We don't want to continue to perpetuate those rounding errors. All right? Questions, comments, problems on number 3? Sweet. Then let's clear our canvas so that we can go to the next question. And I'm going to take these down so I can see what that question is. What is the percent composition of oxygen in Na2SO4.7H2O? Sodium sulfate heptahydrate. Yes, 7. Heptahydrate. I wanted to call it hexahydrate, and I'm like, I know that's not right, so let me not do that. So let me pull these two back up so that we can put that down again. And again, on my scratch piece of paper that I have over here, I need to take Na2SO4.7H2O. And I want to know the percent composition of oxygen. So percent O. In order to do percent O, I need to know the mass of the oxygen and the total mass. Okay, so let's do a count here. How many oxygens do I have in this heptahydrate? Well, I have 4 that come from the sulfate, and I have 7 that come from the hydrate, total of 11. So 11 times 16.00 grams per mole. This is 11 moles. So if I do that math, that's going to give me an answer in grams. Come over here. 176. Now, when I write this, I need to have how many sig figs? Well, 11 is a counter, so we don't worry about that. But 16 has 4 sig figs, so this should be 176.0 grams. Now, if I look at the total mass, I'm going to need 2 times the mass of sodium plus the mass of the sulfur plus this 11 times 16 and some other stuff we're going to get to in just a second. We have 14 times the mass of the H, and this is grams per mole. 2 times the mass of sodium, okay, sodium is number 11, it's 22.99 grams per mole. That's a terrible 2. 22.99 grams per mole. Plus 1 mole times the mass of sulfur. Sulfur is number 16. It has a mass of 32.07. And if I do all of that happy math, which I can do over here, I'm going to add what I just had. I'm going to add to that 2 times 22.99 plus 32.07 plus 14 times 1.01. Now, I do realize that the parentheses are not required. Order of operations says that the multiplication is going to happen before the addition. I get that, but I like to be explicit when I do this just to make sure that I put everything in right. That's the only reason I do it. It is not required. But that gives me 268.19. Okay, 268.19. How many sig figs should that answer have? Well, we had a limitation before, didn't we? Yes, we did. And that was 4 sig figs for that one. But now we have to remember that we're using that 22.99, 32.07, 16, and 1.01 is 3 sig figs. So 268 grams. Okay, so now I have 176.0 or 268. This is grams. This is grams. Multiply that by 100. And that's my percent oxygen. So 176.0, and no, I know that's not required. Divided by that. And it gives me 360.38, which of course is going to give, wait, what the hell? Oh, I added, that's not what I wanted. So let me fix that. And I know that number's not right because it's over 100, so it can't be that. So it's this divided by that. No. Let's just get rid of that and do it. 160 divided by 268. And multiply that by 100. And it gives me 65.67. And of course, because we only have 3 sig figs, that's going to be 65.7%. Okay, so there's that one. All right, well, that was exciting. Let's take a look at 5. So let me clear this. Get this back. I don't know, minimize both of these so we can look at the question. Number 5 says silver is converted to silver chloride by chemical reaction. The original mass of silver is 1.007 grams. Final mass of the silver chloride compound is 1.338 grams. What is the empirical formula of the silver chloride sample? Okay, awesome. I can do that. Me thinks me can do something with this. So I have silver, and that's 1.007 grams. That goes by reaction to a silver chloride, and that is 1.338 grams. Cool. Awesome. And we want to know, what is the empirical formula? What is the empirical formula of our silver chloride compound? Okay. Well, there's a couple ways I can handle this. All right. And the one that we need to use here is to convert the number of grams of silver that we have to moles. And in order to do that, I need the mass of silver. So where the heck is my silver? Takes me a minute to find it. Oh, okay. Silver is 47, has a mass of 107.87. I'm going to have to do the same thing for the chloride. But how much chloride do I have? My total mass, 1.338 grams, minus the mass of the silver, will give me the mass of the chloride. And no, I can't do that in my head. That's 0.331. Okay, so then I'm going to have 0.331 grams mass of the chlorine, which is number 17, is 35.45. Okay, let's take a look at that. So let's do the silver calculation first, since we just calculated the mass of that. We'll divide that by 35.45, and that's going to give me 0.00934. 3 sig figs in the mass that I have, and that's going to, so I'll round to 934. We round up because of the 7. Okay, awesome. And since I didn't leave myself a ton of space, I'll have to do some creative writing here. 1.007 divided by 107.87. That's what I wrote. Geez. That number looks sort of like the other one that I have. 0.00934 if I round to 3 sig figs. Well, technically, I shouldn't round that to 3 sig figs. I should leave this as 335. Because this one is 4 sig figs. That's that number that I have there is 4 sig figs. But does it really matter? I doubt that. They're very close to each other. Now, from a technical standpoint, what you need to do right here is divide this smaller number, the 0.0093335, by the 0.00934. But it's going to come out as a 1-to-1 ratio. A, G, C, L is my empirical formula. Awesome. That's sweet. That's what they asked me for. So now I got it. Cool. That was 5. Let's clear some space. And take a look at 6. What is the molecular formula of an OH complex where the molecular weight is 34.0147 grams per mole and the percent hydrogen is 5.938 or 5.93%? I can talk. Well, let's write some stuff down. And yes, I have the ability to still look at the question while I do this, so it's not that I've memorized all this. So it's an OH complex. I don't really know what that means at this point, but I'm going to write it down because it might make sense to me after I start looking at my numbers. Complex, yes. That's what that's supposed to be. Molecular weight, molar mass equals 34.0147 grams per mole. And then the percent hydrogen, 5.93. Now I'm going to show you 2 ways to solve this. I'm going to show you the easy way first, and then I'm going to show you the more complicated way. And I'm going to put it to you this way. When I was a student, I would have done this the more complicated way. It's a little longer, yes, but then I knew that it was that it was the answer I was looking for. But I'll show you both ways that you can do this. Now I know it's an OH complex, and I'm told that it has a molecular weight of 34.0147. Well, what's the mass of this OH? If I were just to consider that, that'd be 16.00 grams per mole plus 1.01 grams per mole equal to 17.01 grams per mole. Well, that 17.01 grams per mole is not the same as 34.0147. So I know that that formula, the OH by itself, doesn't match. Okay, cool. There is a short way to do this. I take the 34.0147 grams per mole, and I divide that by the 17.019 grams per mole. Now, what am I doing and why? So I took the empirical formula, and I found the mass for that. That's that 17.01 grams per mole. And I know that I have a molecular formula, which is some multiple of that empirical formula, which has a mass of 34.014 grams per mole. 0147 grams per mole. So if I divide the molar mass by the empirical mass, that should tell me the ratio that I need to multiply the empirical formula by to get the molecular formula. Okay, so that's what I'm doing here. And if I do that happy math, 34.0147 divided by 17. Ooh, that's not 17. Sorry. Forget that I can't back up. Darn it, I did it again. And that gives me 1.9999688,419, which is 2. All right. So this calculation gives me 2. That means I need to multiply the empirical formula, the OH, times 2. And of course, what that means is that I end up with H2O2, because that's how that works. Okay, awesome. That's one way to do it. Now, how else could I do this? Well, they told me that hydrogen is 5.93%. So the hydrogen has a mass of 5.93 grams if we assume 100 grams of material. The oxygen then has a mass of 100 minus 5.93. Where did my calculator go? And messing everything up. Sorry. I hate it when I do that. So 100.93 gives me 94.07 grams. Now I can take 5.93 grams. I can divide that by the mass of hydrogen, 1.01 grams per mole, and do that calculation. I can take the 94.07 grams and divide that by the molecular weight of oxygen, 16 grams per mole, and get numbers for both of those. Well, all right, I have the 94.07 here. Let's divide that by 16. And it gives me 5.87. And it's 4 sig figs, so it's 5.879. Okay, that's awesome. Let me come back to my calculator. 5.93 divided 1.01. 5.871. Not exact, but pretty darn close. Now, of course, the way this is supposed to work is I go H 5.871, O 5.879. I divide both of those numbers by 5.871. And that gives me HO. But I already knew that. And so I'm still going to have to go through the same thing that I had to do before to find out that it's H2O2. Now, is any of that necessary? No, absolutely it is not. The thing is, you can still get there by giving you by using all the information that they've given you. If you don't know what that OH complex is, and you know what to do with the 5.93%, then you can still get to where you had to go. You can find that it's the empirical formula. But if you recognize that that's what they're telling you is that that's the empirical formula, then you can do the comparison between the mass of the empirical formula and the mass of the molecular formula and find out what that ratio is. So either way is perfectly fine. Really doesn't matter how you do it. As long as you get to that answer and as long as you provide some way that you got there. So I can follow the logic in both of those. And again, we don't really... Is it really that important that I see how you do this? Well, yes and no. Most of the time, I want to see it because if you didn't get the answer you were supposed to get, I need to see where the mistake happened. If I can see where the mistake happened, then I can probably identify what it is that you didn't understand in that process. Okay, so that's what I'm looking for. Is trying to figure out where in this process did you have a hiccup? Where did you end up going wrong? So that I can talk to you about how do we move forward from that. Okay, so that's what that's for. Questions, comments, problems about any of the questions that we've just done. Okay, cool. Then let's clear all of this and let's see what's on the next slide. Dun dun dun. Oh God, I'm going to review chemical equations. Oh dear Lord. All right. I can review chemical equations. How am I going to do this? Well, remember what we talked about? I talked about making yourself a little table. So I'm going to use the annotation thing here. So hopefully that will work. And I'm going to start with this one. I'm going to come over here and do Mg, O, H. Oh, that's not an H. And Cl. Now, these are not written in any particular order. It's just how I happened to see them and while I was looking at it. It really doesn't matter what order you put them in because you're just using this as a bookkeeping so that you can find what you need to find. All right, so again, doesn't matter how you do it. Now, the first thing that I do is whatever this looks like as it's written, I want to know how many of these things have I got. So let's change colors and come over here and do some stuff. I have 1 mg. I have 1 mg. How many oxygens do I have? Well, I have 2 on that side, 2 on the reactant side, and I have 1 on the product side. So I know that my oxygen is already an issue. But let's keep going for now. I have 2 hydrogens on the react. No, actually I have 3 hydrogens on the reactant side. Got to get both the OH2 and the HCl. And I only have 2 on the product side. So again, O is a problem, H is a problem. Let's talk about Cl. I have 1 Cl on the reactant side, and I have 2 on my product side. Oh dear Lord. Well, Mg is okay, so that's fine, right? But Cl is not okay. I have 2 on the product side and 1 on the reactant side. So let's try and fix this by putting a 2 here. That then changes this 2 . So now I have 2 here as opposed to the 1. Oh, that isn't what I meant to do. Geez. Drag that over there so you can't see it. Sorry. So that should be a 2. We've now changed the 1 to a 2. So realistically, I want to take this number and drag it out of here. Now, is that what I actually do when I write these things? No, really it isn't. What I do is I leave that there and I draw a line through it. Because I know I'm not using it anymore. So I am using the 2 that I've written out here. And that's the one that I need. Okay? So that's what we're talking about for those. Now, I'll drag this out here. So I've changed that. Now I have 2 of those, but I've also changed the count on the hydrogens. So I still have 2 from here, but now I have 2 from here as well, so my total is 4. So I need to change this to a 4. And again, I'm going to cross out the one that I've drawn that I don't need. Okay, sweet. All right, so chlorine is 2 and 2. Magnesium is 1 and 1. Oxygen, I still have 2 oxygens on the reactant side and 1 on the product side. And right now I have 4 hydrogens on the reactant side and 2 on my product side. Well, that doesn't really work now, does it? But what happens if I turn this H2O into a 2? Then I have to cross out my hydrogens that are here. No, not that one. I need to get rid of that. And I need to get rid of that. And now I have new values for these. So my hydrogen, again, is 4. And my O now is 2. Do all my numbers match? No, that's not that one. Oops. So do all my numbers match? Yes, they do. Absolutely, they do. And that means that I have balanced this equation. Okay, so that's the kind of process that I use to do all of these things. Now, I'm going to move a little faster going through the rest of them. Okay, and let's see if we can keep up. So I have 1 Fe on the reactant side, 1 Fe on the product side. So currently iron is fine. I have 3 chlorines on the reactant side, and I have 1 chlorine on the product side. That's not so fine. So I'm going to multiply this by 3. Okay. Awesome. So iron is still okay. Chlorine is now okay. I have 1 nitrogen on the reaction side, and now I have 3 nitrogens on the product side. So let's multiply this by 3 to make that even. So now iron, chlorine, and nitrogen are okay. How many oxygens? 3 oxygens. Oh, and 3 oxygens. Okay, awesome. I have 3 times 5 is 15 oxygens on the reactant side. I have 3, and 3 times 4 is 12. 12 plus 3 is 15. That's balanced. Okay, so that is completely balanced. And again, I would use a table just like this. Every time I change something, I cross the thing out. I mean, it's really hard to do with this. But I cross that out, and that's how I do it. Okay. Hopefully there are no questions, comments, problems. But if there are, please let me know. Let's talk about C2H6 plus O2 goes to H2O plus CO2. So first thing I see is carbon. There are 2 carbons on the reactant side, 1 on the product side. So we multiply this one by 2. I have 6 hydrogens on the reactant side and 2 on the product side. So I'm going to multiply this by 3. Now, carbon is good. Hydrogen is good. I have 2 oxygens on the reactant side. I currently have 7 oxygens on the product side. Now here's the thing. I can do this as 7/2. I can do that as a fraction. It is perfectly okay, because if I do 7/2, then when I multiply that by O2, then I end up with just 7. And that works. It's not ideal, and it's not really the way we like to do things. So let's talk about how we would fix this. I'm going to do one at a time. We would then make this 7. We would make this 2. So we're going to take and multiply the entire thing by 2. All right? That's what we're doing to fix that. That's how I get rid of that fraction. So this is going to be 6. And then this one, instead of being 2, is going to be 4. Now, time for some commentary. Is that necessary? Absolutely not. You can have the fraction in there. It is not a big deal. The only reason that I don't do it is because I know that if I balance this thing, I'm going to have to do calculations with it, and I don't like to do fractions, so I try to get rid of my fractions in the beginning. Okay, that's how I do it, and that's why I do it. All right? Does anybody have any questions, comments, problems about that? I hope not. Give me just a second. Sorry, my notes have gone to sleep. Now the next one that we're going to deal with, and I'll put this back up so you can see it. KMnO4 plus HCl goes to KCl plus MnCl2 plus H2O plus Cl2. Now I haven't been doing this for all of them, but I'm going to do it for this one. You're probably going to want to see how we go through this. So I'm going to have a K, I'm going to have an Mn, I'm going to have a Cl, I'm going to have an O, and I'm going to have an H. Those are all the species that I have. So we need to be able to deal with that. Currently, I have 1K and 1K. I didn't want to move that. I just wanted to do a new one. So 1K, oh, let me do that a different color. 1K and 1K. Awesome. I have 1Mn, I have 1Mn. So far I look good. I have 1Cl, and I have 1, 2, 3, 4, 5 Cls as products. I have 4 oxygens on the reactant side, and I currently have 1 oxygen on the product side. Hydrogen. I have 1 hydrogen on the reactant side, and I have 2 hydrogens on the product side. Obviously, that is not ideal. That is not what we're looking for. So what can I fix first? Well, it looks to me like the first thing that I need to fix is the chlorine. But the chlorine is messy because it appears in so many different places. So let's see if we can fix the oxygen, since that only occurs in one place. So I know that I have 4 oxygens on this side and I have 1 over here. What if I multiply this by 4? Okay, awesome. That's helpful, right? So by multiplying it by 4, I fix the oxygen. Now, that means that I have now gone from 4 oxygen and 1 oxygen over here to 4. All right, and let's just pretend that I've crossed that one out. Okay, but I also changed the number of oxygen or hydrogens too, didn't I? So now we don't have 2 of those. We have 8 of those. 8 hydrogens. Well, let's fix this and put an 8 over here. Okay, now I've fixed that. I have 8 hydrogens. Awesome. And now I have 8 Cl. Okay. So not exactly what I want, but we're headed in a better direction. All right. How am I going to do this? Well, this is a Cl2. This is a Cl. This is a Cl2. And this is an even number. So I'm going to put a 2 out here. Hold on just a second. I'm looking at my notes. So I'm going to fix this by putting a 2 here. Okay, I put a 2 there. Now that means I have 2 Ks here. And I have 2, 4, 2, 4, 6 Cls. Still not what I need, but it's headed in the right direction. But in order to fix this K that I did, I need to put 2 Ks over here. So that now means that I have 2 Ks. I have 2 MNs. I have 2 times 4 is 8 oxygens. Did mess everything up. So instead of needing 4 oxygens, I need to do 8. So that I can fix that. 8, 8, 8, 8. What else did I change? H. I now have 16 H's, right? Okay, cool. Let's fix the H's again. So instead of 8, let's put 16 here. I have 2 K's, 2 K's. 2 MNs, 1 MN. So let's put 2 there. I have 2 of those. I now have 16 H's. Yeah, we got that. And 16 Cl's. That goes to 2 Cl plus 4 Cl. So 2 from here, 4 from there. That gives me a total of 6. And I need 16. So I can multiply this one by 5, and that gives me a total of 16. All right. Two and 2, 2 and 2, 16 and 16, 8 and 8. Oh, wait, H. I have 16 on, oh, I forgot to write it over here. This is 16, and 8 times 2 is 16. Is that right? Oh my god, did I actually do that? 2 KMnO4, 16 HCl, 2 KCl, 2 MnCl2, 8 H2O, and 5 Cl2. Long, ugly process, but it worked. Okay? So that's how we deal with that. And it is way more complicated to do it when you have one species on the reactant side and multiple species that have that one element on the product side. All right? Let's talk about carbon. C3 on this side, C on this side. So let's multiply this guy by 3. Okay? I have 8 hydrogen. Currently I have 2 hydrogen, so let me multiply this by 4. So C3, C3, H8, H8. I have 2 on this side. I have 2 times 3 is 6, plus 4 is 10. So I multiply this by 5, and that should have me even everywhere. Cool? Awesome. I have 1 Al and 2 Als. So let's put 2 over here. I have Fe2 and an Fe over here. So I need 2 of those. O3, O3. Oh my god, I'm done. I balanced them all. Woo! That was exciting now, wasn't it? Okay. So, let me... I'm not going to save them. Okay. All right with that? Let me turn off my annotation. And let's move to our next slide. Oh, dear Lord. This is a lot. Let's see what we can do with this. Nuclear stuff. So what is the formula of an alpha particle? Well, okay, let's talk about alpha particles. So alpha particles can be written as just an alpha, or as a more useful thing, 4, 2, H, E. An alpha particle is a helium nucleus. So 2 protons, 2 neutrons, helium. Awesome. What's the formula of a gamma particle? Well, a gamma particle looks like that. So take this and turn it It's a gamma. It's just energy. That's all that is. Okay. What's a neutron? 1, 0, N. So it's a neutron. It has no protons and 1 mass number for the neutron. Okay. What's another name for a beta particle? Well, another name for a beta is an electron, which we write as E minus. We can also write that as -1 0 E. We can write it as a -1 0 beta. Or just E minus. Okay? So it's an electron. Write the nuclear equation showing the radioactive decay of polonium-218 if the decay produces an alpha particle. Okay, let's start at the beginning. Radioactive decay. So I'm going to start with polonium-218. So 218 has to get written down. And then it's polonium, which is PO. PO. Awesome. And do I know that offhand? No, but that's what the internet's for. So I can look that up on the internet. Now, PO is number 84. So I can do 84 down here. Okay. And that's going to decay. And it produces an alpha particle, 4,2He. But obviously that's not the only thing. There has to be something else over here. So we have to take the 218 minus the 4. That gives me 214. So that's its mass. And I have 84 minus 2 gives me 82. And if I have 82, then what the heck is that? Well, that's lead. So that's lead 214. Okay? And that's how we do that. We start with what they give me, 218, polonium PO. I look up the number for PO, which is 84. I know that it produces an alpha particle, which is a 4,2He. And then this other thing has to be the difference between the polonium-218 and the alpha nucleus. Okay, so that's how we get the 214-82 Pb. Questions, comments, problems on that? Let's stop the annotation. And questions, comments, problems. Okay, now that is the end of our review, all the questions that we were going to do there. So I'm going to stop the recording for this. If you have any questions, comments, problems, please let me know. Again, mention that this is the exam 1 review, the approximate timestamp, and your question about it, and I will do my best to get back to you on that. Okay? I hope that was helpful for you guys to remember not only what you did, but some of the logic that we have in doing things the way that we do. So we're going to start with lecture 4 in just a minute. All right. Thanks, guys. I appreciate it.